Welcome to Lecture 13, The Sun, Part 1. This is an exciting lecture because the title of this course is, as you well know, Stars in the Universe. And it's only taken us 13 lectures to actually get around to talking about stars. I did warn you, to be fair, in the early parts of the, in Lecture 1, as a matter of fact, that it was going to take some time, that we were going to have to lay some foundation, establish a basis on which to build before we could really get into the meat and potatoes. Now, for the last few lectures, I've started to dribble out some of the what I think is a little bit more interesting information. But today we really dig into the central theme of this course, which is, again, stars. And it's appropriate to start with the sun because the sun is certainly is the closest star. It's the star we know the best. And as I've mentioned a few times, it's in many ways a run-of-the-mill, sort of a very standard star, a very normal star as far as the types of stars go that we see in the universe. So there's a lot to be gained by starting off with it. And to that end, we're actually going to spend 3 lectures talking about the sun and use that as a place to start on and build to spend quite a bit more time talking about stars that are not the sun. So with that preface, welcome again to Lecture 13. Glad you're still here as we dig into really the central theme of the course, and let's begin. So as I've mentioned, and as you know, the sun is it's a star, a ball of plasma. Remember, if you remember nothing else from this course, stars are not made of gas, right? They're made of plasma. The sun is a star, and it's the nearest star to us. And that's why we know it the best. So one thing that we did say from very early on as we began classifying things in the universe and thinking about the way that we organize objects in astronomy, we made a distinction between stars and everything else, right? And so the stars generate their own light in a way that nothing else does. So we've touched on this just in passing. But today we're really going to dig into the details and talk about why the sun shines. Well, there are a few different ways to answer this question. But at some level, all you need to know is that it's hot, right? Because as we've talked about, everything that's not at absolute zero generates electromagnetic radiation. And, you know, we spent multiple lectures talking about Boltzmann distributions, black body radiation, and how through Wien's law and the Stefan Boltzmann law, we can learn a lot about the temperature of an object just by looking at its spectrum. So at some level, stars shine and they give off visible electromagnetic radiation just because they're hot enough to do so. But on this slide, I say that I stress the fact that the sun is both hot and dense because we're going to be interested today in digging a little bit deeper beyond just saying, yeah, the sun is hot. Its surface is around 6,000 Kelvin. We want to understand, how did it get that way? And one of the keys to getting that way is that the sun had to be just extraordinarily dense, much denser than anything that we encounter here on Earth. And so we're going to see why that's important. So the sun, as with almost anything of any significant size, has structure. And while we can be a lot more detailed than this, this is going to give us a good starting point. So in particular, there are going to be 3 main regions that we will divide the sun into. So starting from the interior, we have the core. And the core is what it sounds like. It's a relatively small spherical region in the center of the star. It's the hottest region of the star. For the sun, it's a little bit shy of 16 million Kelvin. So remember, the surface is just under 5,800 Kelvin. 5778 is a very precise number, which is plastered here on the slide. Sometimes we round that up to 5,800. Sometimes we round it up to 6,000. But it's thereabouts. So you can see you go from about 6,000 at the surface to almost 16 million in the core. So the temperature changes a lot as you go down into deeper and deeper into the sun. But in between the core and the surface, then there are a couple of other regions. One is working your way out from the core is what's called the radiative zone. And continuing our theme of not being very creative in our naming schemes, it's called the radiative zone because the main mechanism of energy transport in the star in that region is radiation. So in other words, energy is produced or is released is a better way of actually saying it. Energy is released in the core, and that energy then moves out towards the outer, towards the surface of the star. As it leaves the core then, the primary means through which that energy is transferred is radiation. Just electromagnetic radiation is moving through the radiative zone. But at some point, that changes, and you enter what's called the convective zone. And in the convective zone, as you might guess, rather than radiation being the main means of energy transport, energy is transported primarily through what's called convection. And we'll talk in more detail about radiation versus convection and methods of energy transport. For right now, though, it's just these are names that we use to label the different regions of the sun. Again, just dividing them up based upon what the main mechanism by which energy is moved from one place to another. And remember, the energy is being released in the core. That's why it's the hottest, densest part of the star. And then the energy is moving from that core out to the surface. And then eventually, once it gets beyond the surface, it streams out into space and moves mostly just through the vacuum of interstellar space, with a few interesting exceptions, like when it lands here on Earth for us to observe. So we'll get into more detail, but at a high level, this is the large-scale structure of the sun. So now we know that, and we'll go into a lot more detail, but we've got this nuclear furnace, in the center where all this energy is being released. Why does the sun stay hot? Why doesn't it just cool off? Because as you know, if you take a hot object and just sit it here on a table, it's going to cool off over time. In order to maintain its energy, there needs to be a continuous energy source. What is that energy source for the sun? Well, the key is something that I mentioned to you before. I think there have probably been at least a slide or two that have mentioned it so far in this course, but today, again, we're going to get into the details. The answer is nuclear fusion. Fundamentally, this is what defines a star. A star is a ball of plasma whose energy source is nuclear fusion in the core. Okay, so if you have nuclear fusion going on in the core, then you're a star. And if you don't, then you're not. So, for example, the composition of Jupiter is very similar to the composition of the sun, which is a point that we made in the past, but there's no nuclear fusion in the core of Jupiter. So it's a planet, the sun is a star. Once that energy is released through the nuclear fusion in the core, then it travels. And it travels and that energy is transported in different ways, as I mentioned. It's transported primarily through radiation as it leaves the core, but then eventually that primary process transitions over from radiation to convection, and so we call it the convective zone. As these arrows indicate, the convective zone is dominated by convection, which, as we'll talk in more detail, just means fairly large-scale fluid flow. Hot air rises, cold air falls. That's an instance of convection. Well, same thing is true in a star. Hot plasma rises, cold plasma falls, right? And so that's kind of what these arrows indicate. One of the keys to understanding the sun's structure is the concept of hydrostatic equilibrium. And while it's a fancy term, maybe, it really is what it sounds like. So hydro just means, it's short for hydrodynamic, which means that there are fluids involved. And you may or may not think of a plasma as a fluid, but it's not a solid, so it's a fluid. Static means things are at rest, at rest. And equilibrium is a term that we've run into before. It just means that on a net basis, nothing is changing. So when we describe a star as being in hydrostatic equilibrium, we mean that it's not growing, it's not getting bigger, it's not shrinking, it's stable. And so the concept of hydrostatic equilibrium is key to determining what a star's size will be. And fundamentally, it all comes down to two different forces balancing one another. The first, is gravity. Gravity, in fact, is responsible for the formation of a star to begin with, which, if you hold on for a couple of weeks, we'll come back to. Right now, we're talking about the sun. Once we get past, we get a better understanding of how stars work once they become stars, we'll actually back up and talk about stellar formation. But as with so much of astronomy, gravity is the force responsible for the star's formation. And if left to its own devices, gravity would just collapse the star down to zero size, right? Because gravity is always an attractive force. So something has to be balancing that tendency to collapse. Why isn't the sun just collapsing, down to a point? And the answer is internal pressure. So there is some source of internal pressure that's generated at some point, and we'll talk about that, that balances eventually the gravitational tendency to collapse. And so a star's equilibrium size is determined by the balance between these two forces. You have gravity tending to make the star collapse. You have an internal pressure, which is counteracting that. And where those two forces are equal to one another, the star will reach equilibrium. But what is it that's responsible for a star's internal pressure? So it turns out that the source of a star's internal pressure is critical. It's absolutely central to determining the star's properties. And as it turns out, the answer to this, both what is responsible for that internal pressure and the details of that pressure, change throughout a star's lifetime. And so we're going to go into some detail about that as we, several weeks from now, as we look at the life cycle of a star. And we'll see in some detail how, as a star goes through different stages in its evolution, what is providing that internal pressure will change, and as a result, the size of the star will change. A main sequence star's internal pressure, though, which is what we're going to focus on right now, because we're focusing on the sun, and the sun is a main sequence star. The internal pressure for a main sequence star is generated by light. And that light is created in the process of nuclear fusion. So remember, nuclear fusion is the defining characteristic of a star. The nuclear fusion in the star's core is what makes it a star. And light that is generated in that fusion process exerts a pressure. You don't normally think about light as exerting a pressure because the intensity of the light that we encounter in our lives is quite small. But the intensity of light encountered in the core of a star is astronomical, no pun intended. And so the light there actually generates a huge pressure, which is sufficient to counterbalance the gravitational force, which is tending to make that star collapse. So remember, I have made the caveat here, this is a main sequence star. So when we go on and we talk about non-main sequence stars, whether they're giants or supergiants or white dwarfs, we'll need to come back and investigate this question again. But for right now, we're going to focus on main sequence stars. So gravity is tending to make it collapse, and the internal pressure is generated by light. So here's the HR diagram again, which we introduced fairly recently, and this is the real data, right? And the sun is, right where it was last time, right here, very much in the middle of the main sequence. So it's finally time, now that I've told you that nuclear fusion is what's responsible for a star's energy. It's the source of energy, and it's the thing that is ultimately responsible for making a star a star. It's time to finally dig into the details and say, what is nuclear fusion? So to answer that question, we're going to start off with the simplest element there is, the simplest atom there is, the hydrogen atom. And at a cartoon level, this is what a hydrogen atom looks like. It's got a proton in the nucleus, and it's got an electron, which is attracted to that proton through the electrostatic force. And so that this together, they form a neutral hydrogen atom. But as I've mentioned many, many times, the sun is much too hot for neutral atoms to exist, except in the upper reaches of its atmosphere. So in the sun proper, as in any star, it's too hot for atoms to exist. Instead, all of the atoms are ionized, the electrons are stripped away from the nuclei, and that's what makes it a plasma. So an ionized hydrogen atom is a fancy way of saying a proton, because once you take the electron away, all you're left with is the nucleus, and a hydrogen atom's nucleus is just a single proton. So nuclear fusion is going to be it's the combining of nuclei. And so in order to have nuclear fusion, you need to have at least a couple of nuclei. So we'll look at the simplest case where we have two hydrogen nuclei, two protons. Now, protons are positively charged, and as you probably heard, likes repel, at least in the world of electrostatics. And so if you just have two protons near each other, they will repel each other fairly strongly, as a matter of fact, and they'll fly off, until their separation gets, infinitely large, and they no longer experience a force. But if we want to have nuclear fusion occur, that means that we've actually got to get these nuclei very close to one another. And that's not easy to do. So if you have slow-moving protons, if you imagine having two protons here and you fire them out of proton guns towards one another, how close they approach one another depends upon how fast they were shot together, right? If you just shoot them very slowly towards each other, then they won't get close at all. They'll repel each other. They'll turn around and fly off again. In order to get them close enough for nuclear fusion to occur, these things have to be moving very, very quickly. Now, so the question is, how do we get these things to move quickly? Well, one option is to use a gun, as I just said, or what amounts to a proton gun. As it turns out, we do that in particle accelerators around the world, but it's not a very good way to create a sustained volume in which reactions can occur. And certainly, stars don't require particle accelerators. So what do stars do? Well, stars are ridiculously hot. Right. So, I mentioned, if you remember, it's been a few lectures back now, but temperature is just a measure of the average kinetic energy of a particle. Or said another way, it's a measure of the speed at which particles are tending to move. So as you heat an object up, that means the particles in that object are moving faster and faster. And so as you heat a ball of gas up, it means those gas molecules are moving faster and faster. As you heat a ball of plasma up, it means that those particles and nuclei and electrons are moving faster and faster. And if you get high enough in temperature, those protons eventually will be moving fast enough that they can get close enough, even given the electrostatic repulsion that they feel, they can get close enough for nuclear reactions to occur. And that's the key breaking point between something that's not a star and something that is a star. Jupiter, I keep coming back to it, but Jupiter is very much like the sun in terms of its composition, but it just never quite got hot enough for nuclear fusion to begin. Whereas the sun, as it turns out, because it's more massive than Jupiter, and we'll talk more about that, the sun did get hot enough in the core for these protons to get close enough to one another for nuclear fusion to begin. And once that happened, immense amounts of energy are released, it cascades, and a full-blown star is born. So that's the key to initiating nuclear fusion in a star, to creating a star, is having a hot enough core that these protons can get close enough together for fusion to occur. But what is this? What is the detailed fusion process then? Well, it turns out that there are a number of them. But this slide right here is indicating one of the most important processes, and one that we're going to focus on, which is the reaction between two protons, which creates what's known as a deuteron, as well as subatomic particles known as a positron and a neutrino. So we'll spend a fair amount of time talking about the details here. But fundamentally what's happening is these two red particles represent protons, they combine. One of those protons turns into a neutron, which is gray here, and as a result of that transmutation, that conversion of a proton into a neutron, a positron and a neutrino are born, if you will. A positron is the most famous case of antimatter. It is the antimatter pair particle to an electron, which means that it is almost identical to an electron in every way, except that its charge is reversed. So electrons are negatively charged and positrons are positively charged. But otherwise, a positron is very, very similar to an electron. It has the same mass as an electron, and has essentially the same other subatomic, other characteristics of subatomic particles as well. The neutrino is, as its name indicates, is a neutral particle. It's extremely light, extremely low mass. I mean, you think about protons as being small. You think about electrons as being even smaller in terms of their mass. Well, neutrinos are way smaller, way less massive than either protons or electrons. And for most purposes, we can ignore them. It turns out that they are important, and in particular, for our purposes, they're going to come back, and we're going to have to think about them in the context of supernova or stellar explosions, which in several weeks we will have some time to talk about. So hold on to them. The neutrinos will be important, but for most of our purposes, and for example, when dealing with the energy release of fusion in the core of the sun, we're not going to be particularly worried about the neutrino. But so this is the dominant fusion process, the beginning, the first step in the fusion that occurs in the sun is this combining of two protons into again, this particle is known as a deuteron or a deuterium nucleus. It's another flavor of hydrogen, an isotope of hydrogen, which we'll talk more about. But this is the beginning of the fun, which makes the sun the sun. It's also worth mentioning that it is the strong nuclear force which is responsible for holding nuclei together. So I think I have mentioned in passing, though it's been some time, and you may have heard this elsewhere, there are four fundamental forces in nature that we know of, which are gravity, electromagnetism, and the strong nuclear force, and the weak nuclear force. So, as I've said many times, we run out of clever names, and so the names don't end up being very clever. But the strong nuclear force is the force that's responsible for holding nuclei together. It's responsible for protons and neutrons having the properties that they do, and it's responsible for holding those protons and neutrons together in nuclei. Fundamentally, then, it's also responsible for the nuclear reactions that occur, or for describing the nuclear reactions that occur in the nucleus and the fusion that powers the stars. So, before leaving this slide, the last thing that I want to highlight is that every chemical reaction that you have ever witnessed or thought about, or if you haven't thought about any, think about some now. Every chemical reaction is involved with the exchange of electrons. So the nuclei in chemical reactions don't change, but electrons are exchanged from one atom to another, from one molecule to another, and as those exchanges occur, energy may either be released or absorbed, depending upon the details. But the nuclei never change in chemical reactions. In contrast, in nuclear fusion, it is the nuclei themselves that are interacting. So protons may be transformed into neutrons or neutrons into protons. You may have two nuclei collide and exchange some nucleons, exchange some protons or neutrons. And as a very general rule, the energy that is released in nuclear reactions is much, much, much larger than the energy released in chemical reactions. In exactly the same way that a nuclear explosion is so much more energetic than a conventional, even a high energy chemical explosion. So keep in mind, chemical reactions, they're great for chemistry, but that's not what we're interested in. What we're interested in, what fuels the stars, are nuclear reactions in which the nuclei themselves are interacting. So let's come back to these interacting protons. When two atomic nuclei, and in this picture it's protons, but it could be something different, and in time we will talk about the fusion of things other than protons. When two atomic nuclei are moving fast enough that the strong nuclear force can overcome the electric repulsion, that's when nuclear fusion occurs. But as we mentioned a couple of slides ago, in order for that to happen, these protons have to be moving very quickly, which essentially means they have to be very hot, because the electrostatic force acts at much larger distances than the strong nuclear force does. And I'm going to say that again because that's actually critically important to understanding how, why stars behave the way that they do, why fusion has the properties that it does. The positive charges and protons repel one another even at relatively large distances. But the strong nuclear force only acts over very short distances. And so if I held two protons here, they would repel. I need to get them close enough that the strong nuclear force can act in order for fusion to occur. If I do that, if I get those protons close enough that the strong nuclear force begins to act, then it's much stronger than the electrostatic repulsion. Okay, but again, I have to get them close enough in order for that attractive strong nuclear force to occur. When this happens, though, if I can do that, then as I've said, one of these protons gets converted into a neutron, and in that process, a positron and a neutrino are produced. And as I mentioned before, and you'll read in the readings, the result here, this nucleus, this new nucleus that we've created that consists of one proton and one neutron, is known as a deuteron, or a deuterium nucleus, which is an isotope of hydrogen. It's not the normal hydrogen. It's not the most common form of hydrogen. The most common form of hydrogen has a nucleus which is just one proton, as I've said. But, as I also said, and as you can look, if you pull up your favorite version of the periodic table, you can look that every element is defined by the number of protons in the nucleus. So a hydrogen atom, or a hydrogen nucleus, by definition, is one that has one proton. A helium nucleus has 2 protons. A lithium nucleus has 3 protons, and so on. But the number of neutrons may vary. So most commonly, hydrogen nuclei have no neutrons. But it can have 1 neutron, and here it does. So we've taken 2 hydrogen nuclei, simple protons, merge them together, and through this nuclear reaction, we produce a new kind of hydrogen nucleus known as deuterium, or a deuteron again. This positron, just to reiterate what I said recently, is very much like an electron. You can think of it just as a positive electron. You need to have something positive flying out here because the electric charge is a conserved quantity. So just like energy is conserved in nature, it's neither created nor destroyed, it just changes form. Electric charge is neither created nor destroyed as well. And so we started off with 2 protons, both positively charged, so we have 2 positive charges. We need to end this nuclear reaction with 2 positive charges. And so when one of the protons gets converted into a neutron, which has no electric charge, well, we've got to get rid of, we still have 1 extra positive charge that's out there somewhere. It turns out that in this particular reaction, it's out of the picture by a positron. This neutrino, as you might imagine, because it's so light and it's electrically neutral, it's extremely hard to detect and actually went undetected for a long time. But it is there, and it's important to keep it in mind for a few different reasons, not least of which is that if we want to correctly describe stellar explosions, as we will in a few weeks, we're going to need to keep track of these neutrinos. But again, this is an up-close and personal visit with the first nuclear fusion process that we're going to be interested in. 2 protons gives us a deuteron, a positron, and a neutrino. So what type of nuclear fusion powers the sun? We've seen one particular nuclear reaction that's going to play a key role, but we can generally say that in the case of the sun and in all main sequence stars, the nuclear fusion that provides the internal pressure that stabilizes the star against gravitational collapse is a process by which hydrogen nuclei are converted into helium nuclei. And as this happens, what the star looks like will change. When a star is born, it consists of almost entirely hydrogen, because that's what most of the universe is. But as the nuclear fusion takes over and begins in the core and goes on for longer and longer time, more and more of the hydrogen is fused together to form helium. As that happens, the core is converted from a hydrogen core into a helium core. And the size of the core, or the size of the amount of helium in the core, grows. Eventually, you get to the point where all of the hydrogen fuel, which is in the core, is gone. There's no more hydrogen to fuse in the core. So what happens? Well, that last question was actually a teaser because we're going to wait for a week or two to actually answer the question of what happens when all the hydrogen is eliminated from the core, because it turns out that that's a dividing line between stages in a star's life. Right now, we're going to ask in a little bit more detail, how does this fusion process release energy? I've made the claim that stars are defined by nuclear fusion occurring in the core, and I've made the claim that just a profound amount of energy is released in these nuclear reactions, something that somehow generates almost 16 million Kelvin temperatures in the core. But where is this energy coming from? Because if energy isn't created or destroyed, somehow it's just being converted from one form to another. So what form was it in before it was released and produced these huge temperatures? Well, it turns out that the answer is that energy was frozen in the form of mass. And so let's see exactly what that means and what that looks like. We're going to go into more detail, and I keep telling you this, but we're going to go into more detail in the lectures to come about the specific series of nuclear reactions that actually occur in the sun. You've seen the first one already, where protons fuse to form a deuteron. But at a high level, I've told you already that hydrogen is fused to form helium in main sequence stars. And so a helium nucleus consists of 2 protons and 2 neutrons, as is sketched here on the right part of the slide. But we know that a star begins its life almost entirely composed of hydrogen. And so at some high level, what we're going to have to do is combine 4 hydrogen nuclei, or 4 protons, and produce a helium nucleus. And we're going to have some series of nuclear reactions that occur to make that happen. But let's consider the following. If we start off with 4 protons, we could ask, how much mass do those 4 protons have? And it turns out that it used to be harder, but now you can just Google it up and find out what a proton mass is. It turns out that because they're quite small compared to anything we visibly interact with on a daily basis, it's not very convenient to measure proton masses in kilograms or grams. And so the typical unit for measuring subatomic particle masses, or one typical unit, is what's called an atomic mass unit, or AMU for short. And so one atomic mass unit is close to a proton mass, but not exactly. And so if you look up the precise number, the mass of 4 protons is equal to just a little bit more than 4 atomic mass units. And that's fine. So now let's ask the following question. Well, we're going to combine these 4 protons and produce a helium nucleus. What do you think the mass of a helium nucleus is? Well, you could be forgiven if you were to guess 4.0291 AMU. But it turns out the scientists have done very detailed measurements, and they have a very precise and accurate number for the mass of the helium nucleus, and it happens to be 4.0026 atomic mass units. So if you had just kept 1 digit after the decimal, you would say, aha, 4 hydrogens are 4.0 AMUs, and 1 helium nucleus is 4.0 AMUs. It makes sense, mass is conserved. But it turns out that thanks to our very precise measurements, we know that in fact that's not true. In fact, the 4 hydrogen nuclei have a slightly larger mass than does the helium nuclei, or nucleus. So what happened? Where did that extra mass go? Well, as you might now expect, I've hinted at it a few times, that extra mass is actually released in the form of energy. And so this is why sometimes people refer to mass as frozen energy that usually stays as it is. But in nuclear reactions in particular, that mass can be converted into other forms of energy and released. And that's exactly what happens in the star. What do you think the relationship is between the mass that is converted to other forms of energy and the amount of energy released. Well, feel free to pause me for as long as you like if you want to ponder that question. It's one of the most famous equations in all of physics, and it's one that almost all of you will have encountered at some point just in pop culture. And that's Einstein's famous equation, E equals mc squared. In this particular case, I've written it as delta m because delta, capital delta, the Greek letter is used in physics and mathematics to denote change. And so what I mean here is that the energy that's released in this nuclear reaction is equal to the change in the difference in the mass. So how much mass did we start off with minus how much mass we ended up with. Delta M is that difference. So this is the amount of mass that has been released in the form of energy. And we then multiply that by c squared, where c, as you know, is the speed of light. Now, if you recall, the speed of light is really, really big. And what happens then, if you take a really, really big number and square it, multiply it by itself, you get a really, 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 really big number. The upshot is that even a small amount of mass, when converted into energy, when released in the form of energy, releases a very large amount of energy. And fundamentally, this slide is the best summary you will see, at least today, at least for me, of why nuclear fusion is such a powerful and such a powerful thing, both in terms of powering stars and in terms of potentially powering Earth, if we can ever find a way to harness nuclear fusion for our purposes. Because again, taking even just a small amount of mass, if we can convert that into usable energy, it's a huge windfall in terms of energy. And as I might point out on the subject of energy production on Earth, hydrogen is really easy to come by because the majority of atoms well, on Earth, certainly in our oceans, are hydrogen atoms. So this is the, it's a great place to end this lecture because this slide really encapsulates the take-home message here, which is that nuclear fusion releases energy by converting mass into other forms of energy, which are kind of shown here. We have these squiggly lines indicate electromagnetic radiation or light. This positive charge here is a positron that we've met before and we'll talk more about. Just you can think of it again as a positive electron. And then these neutrinos that fly out as well. So energy is carried off in different ways, in different means, and we'll talk about that, how that energy is transported going down the line. But again, this is it. Nuclear fusion releases energy through the conversion of mass to other forms of energy, and mathematically that connection is given by Einstein's famous equation E equals mc squared. So this lecture and the couple to follow are going to be a little bit shorter than some of the lectures that I've given you. I hope that won't bother you too much. But for better or for worse, they can be dense. There are a lot of new concepts here. As I said, we're really now into the meat and potatoes of the class, where we talk about stars and the universe, which is what this class is all about. So thanks for sticking with it. If as always, feel free to reach out to ask any questions that come up. Feel free to rewind and watch the highlights again. And in the meantime, I will look forward to meeting you back here again for lecture 14.